So good morning and welcome to the second Global EV Charging webinar event. And this time we're focusing on EV charging best practices and power quality. And during this 2 days event, the focus on the first day will be on this EV charging best practices. So this day you can learn about the experiences from other experts on the ways to improve the charging experience for the customers. And the second day we'll be doing a deep dive into power quality and the effects of modern devices like EVs on this power quality. It is still possible to register for all the webinars via our website. And all the webinars will also be recorded and uploaded to our YouTube channel. So keep an eye on our YouTube channel and please subscribe if you want to receive notifications. During the event, Tim Slange and I will be hosting the webinars. And during each webinar, one of us will be the host and the other one will be monitoring the questions log. And he will be selecting the questions to be answered after each presentation. So if you have any questions, you can find the questions box in the GoToWebinar tool. It's a little drop-down menu. You can open it and you can ask your questions over there. So that's it from my side now. So now, without further ado, it is my pleasure to announce our keynote speaker, Mark McGranaghan. He's a founding partner of EPRI, the Electric Power Research Institute, and he will present on the changing nature of power quality and compatibility. Okay. Okay, Mark, can you
okay, there. Just taking a little bit of time there to get unmuted. I apologize. Go into presentation mode. How does that look? Can everyone see the title slide okay?
Yeah, it's excellent.
Okay, great. Thanks, Thijs, and thanks to the all the conference organizers for this opportunity to kick things off, talking about power quality, and I'm going to focus on the term compatibility as we talk about this. My name is Mark McGranaghan. For those of you that don't know me, I've been working in the power quality area for virtually my whole career. When I got out of school with my master's a long time ago, back in 1978, my first project was working on a harmonic analysis software for evaluating the flow of harmonics on distribution systems, and eventually became a software program called VHarm and SuperHarm that we used for many years for harmonic studies. So I've been working with a vendor, McGraw-Edison, became Cooper Power, and then a consulting company called Electrotech. And since 2003, I've been with the Electric Power Research Institute in our transmission and distribution research area. We started a power quality program at EPRI back in the 1990s and have been doing a lot of research in the power quality area over these years. So I'm really delighted to be able to chat about power quality and compatibility here this morning. And I'll look forward to the questions and thoughts from all of the attendees here this morning. Looks like a great group of people on the webinar. So this is just an outline. We're going to talk about compatibility. I think power quality is all about compatibility, and it's very timely as we embark on a energy transition that involves electrification of so many other energy systems, especially electric transportation, that these concepts of compatibility are going to continue to be absolutely critical. So we'll talk about a little bit of history, some of the traditional concerns that we've worked on in terms of power quality, and then then discuss what's changing, what's new, what do we have to think about in terms of research priorities going forward. And I'll kind of do a quick focus on the role of power quality monitoring. I think that's particularly important as we go forward, and new technologies like artificial intelligence and data analytics become more prevalent, and power quality is no exception to that. And then I'll just highlight the need for collaboration as we go forward. That's always been a hallmark of power quality activity in the industry, is working together between electric utilities and technology providers and industrial companies that have power quality issues. So very exciting. This is a picture of a book that Roger Dugan and Surya Santoso from the University of Texas and I have written. We're on our 3rd edition, so try to get some of our thoughts down on paper over the years. All right, compatibility. What are we talking about? This is a diagram that we came up with as we were working in the IEC standards for power quality to describe a lot of the concepts that are now incorporated into IEC 61000-3 series of standards. And it just illustrates that power quality is not a binary thing where it's okay or it's not okay. It's a very much a statistical characterization of power quality phenomena on the power system and on its impact on equipment. So we have to get this balance between managing the power quality disturbances, which could be harmonics or transients or flicker or voltage variations, those disturbances, and then on the other side, the ability of equipment to deal with those disturbances. So it might be difficult to keep harmonic levels below a certain level on the power system. So we have to allow some amount of harmonic distortion, and we have to make sure then that equipment can work properly with that amount of harmonic distortion. Same principles for other power quality phenomena. And I think what I'll do is just use 2 examples of historical investigations, one harmonics and one voltage segs, just to illustrate these concepts of power of compatibility in kind of the 2 different categories of power quality disturbances. One category is what I call steady state disturbances, or power quality variations that are kind of there all the time, like voltage variations, flicker, and harmonics are in that category. And then disturbances that are based on kind of individual events, like faults on the power system that result in voltage sags or lightning transients. And so we'll just take a look at compatibility in the category. We use harmonics and we use voltage sags to illustrate those 2 categories of how we've worked on this historically. And for the harmonics, I picked a study that was done by Nuon in the Netherlands back in the 1990s. 1990s kind of a really important period of investigation and research into harmonic issues. And this was a really interesting chart that Nuon came up with, looking at summer and winter conditions and harmonic distortion levels on the system. And you can see on the chart on the left that in the summer, that when there wasn't so much heating load, which provides damping of resonances, the harmonic levels were quite high, reaching over 4% at the 5th harmonic and over 5% voltage distortion during many periods. And the levels were really related to resonances created by capacitor banks on the grid. And you can see on this next slide that as we switched in capacitor banks and switched off capacitor banks, you could see where those capacitor banks impacted the resonance conditions on the system, and in particular the 5th harmonic, that for certain amounts of capacitors on on these large banks that were on the transmission system were causing resonances. And when we got into those resonance conditions, the voltage distortion got quite high. So the solution to avoid the resonance conditions was to convert some of these capacitor banks into harmonic filters. So we tuned the capacitor banks with a reactor, and that creates a series resonance or a filter at that near that fifth harmonic, and moves the parallel resonance that magnifies the harmonics below the fifth harmonic, where there's not so much harmonic generation from rectifiers and that are in front of TV sets around the grid. Just one more example. This happens to be an example from Carolina Power and Light, which is now Duke Energy, converting a substation capacitor bank that was also causing fifth harmonic resonance on a circuit that had industrial loads that generated some fifth harmonic. And you can see when it's switched in how effective it is at reducing the voltage distortion levels on that distribution system. So we learned a lot over the years of how to apply filters and how to avoid resonance conditions, but this really illustrates how compatibility is a coordinated issue between harmonics that are generated by nonlinear loads, and electric vehicle chargers are examples that we'll come back to on this, and the response of the power system in terms of creating resonance and solving those problems. So many years of research have gone into this. IEEE standards like 519, the IEC 61000, series 61000-3-2 and 4 and 6 all deal with compatibility, starting with making sure we don't inject too much harmonics with nonlinear loads like electric vehicle battery chargers, but also making sure that we don't create resonances that magnify those harmonics. So come a long way in harmonic analysis, but still an area of ongoing research. Let's take a look at another phenomena that's important for compatibility, and that's voltage sags. And it's very important for a wide variety of industrial customers, especially with process equipment loads, that if any part of the process trips or is impacted by a disturbance on the power system, it can shut down the entire process and have major economic impacts. So voltage sags is an example of a power quality disturbance that involves technical analysis, equipment immunity, and economics. How much does it cost every time we have an impact to the process, and can that justify investments to make that process more immune, whether it's for UPS or ride-through device, or just buying new controls that are less sensitive to voltage sags, or providing local protection. And we developed a chart after investigations with hundreds of companies, semiconductor companies, plastics companies, food processing. Any process industry has these impacts from voltage sags, and we can solve problems by reducing the number of faults on the power system. That's great, and we don't have voltage sags. But you can't eliminate faults completely. So we do have to look at plant level and machine level solutions to voltage sags, and that's what we illustrating all the different places that we can invest in solutions and do the economic analysis. And we came up with a concept that we call the voltage sag area of vulnerability. So that kind of illustrates an area where faults could occur on the power system and create enough of a voltage sag that it would impact equipment and customers' processes. And then we could use historical data and short circuit analysis to estimate the number of voltage sags that a customer might experience. And that goes into the economic analysis then. So the analysis is understanding how many voltage sags might occur based on historical data. And then we have to look at the sensitivity of equipment, and that we often use one of these voltage magnitude and duration charts to illustrate the capability of equipment to ride through voltage segs. So we have curves with a CBEMA curve developed by the Computer and Business Equipment Manufacturers Association. Back in the 1990s was the first equipment sensitivity curve. Now we have the SEMI 47 standard that's shown here, and other standards that help achieve better compatibility, and we can chart events that occur due to faults on the power system versus the equipment immunity and estimate the number of times that equipment will be impacted. So another example of compatibility, faults on the power system and investing to reduce the number of faults, and equipment immunity that might involve investments as well. And in the end, it's an economic analysis. So that's very important. So that's the concept of compatibility illustrated with a steady state power quality variation like harmonics, and then also with a disturbance type of event, or individual events illustrated with voltage segs. So hopefully that makes sense. And that's been going on for a long time. It's still going on. Still, those are critical power quality issues, but things are changing. Things are changing. We've got this concept of an integrated grid. We're in the middle of an energy transition where we need to integrate more and more distributed resources. So these power quality issues became something that we had to address with solar inverters and energy storage devices, and now electric vehicle chargers everywhere. And we have to make sure that we don't create new power quality issues, and that we have the tools to investigate the issues that do come up. And just mention here that as we've put in place standards for the amount of harmonics that can be created by new loads like electric vehicle chargers or PV inverters or energy storage inverters. And we've done a pretty good job of making these devices better in terms of harmonic generation. And to do that, we've used technologies like pulse width modulation that move some of these concerns up to higher frequency harmonics. We call those supra harmonics in the range of 2 to 150 kilohertz. So we'll take a look at that, the importance of these higher frequency harmonics as we go forward. And so the characteristics of the grid in the energy transition, this integrated grid concept continues to change, and there's more issues of compatibility to deal with as we go forward in the power quality world.
I wanted Dr. Grayson.
Excuse me, my wife has it. So that's things are changing, and there's still a lot of things to be working on. One of the important concepts that I think applies to power quality and many other characteristics of increasing penetration of new equipment on the grid is a concept of hosting capacity, and it's one that we've applied to photovoltaic systems now around the world. It's very commonly applied in the US, where the utility does analysis of each distribution system to evaluate how much photovoltaic inverters can be incorporated on that distribution system. And this is an example of a chart like that, where the hosting capacity limiting factor might be voltage. And as we get more and more PV on a distribution system and it's generating energy during the day, it can result in a voltage rise on the distribution system as that current flows from the PV inverters, the PV generation back towards the substation. And at some point, that voltage rise exceeds our limits, which might be 105%. And that kind of illustrates where the for the current design without implementing new voltage control measures, which might include the characteristics of the inverter itself, we can estimate how much PV we can put on that distribution system without causing problems, and maybe the interconnection evaluations are much simpler up to that point. So that's a concept that's being applied everywhere, and we can apply that same concept to energy storage or electric vehicle chargers. Electric vehicle chargers would be just kind of the opposite from a voltage impact point of view. As more cars are charging and load is being drawn through the distribution system, we can look at the point where the voltage drop becomes more significant than we can accept, and we would have to do something to support the voltage, reconductoring, new transformers, voltage regulators, to be able to handle more electric vehicle chargers on that circuit. So the concept of hosting capacity will be a very important one going forward, that will be part of our distribution planners toolkit, looking at these new kinds of loads. I like to look at energy storage in particular. Energy storage is a very exciting source of flexibility as we integrate more renewable generation with the grid. That energy storage can go at substations, it can go in communities as part of a microgrid, or it can go in individual buildings or homes. So many different places for energy storage. And the beauty, as we get energy storage further out into the distribution system, we get multiple value streams that are possible for that energy storage. So by moving the energy storage out to individual buildings, it can be part of resiliency solutions, it can be part of voltage management solutions, it can be part of strategies for minimizing energy costs and taking advantage of periods where the price of energy is cheaper, and it can be used to integrate more renewables. And I think it's very related to the discussions in our webinars here this week, because electric vehicles are basically an energy storage device, and it's one of the big research areas is looking at the opportunities to get more, to take advantage of that energy storage potential to provide flexibility to the grid, whether it's through control of the charging as a load or even as a vehicle to grid application. So, and the other thing that's happening with electric vehicle chargers that I think is very important as we look at applying more fast chargers and extremely fast chargers with very high megawatt level power ratings, those will often be installed with energy storage so that we can minimize the impact on the grid and the capacity requirements of those energy storage devices. So if we have a fast charger that's integrated with energy storage, we have to look at all the potential for that combination to provide flexibility services to the grid as well as electric vehicle charging potential. So very exciting time for energy storage in general, and especially how it relates to electric vehicle charging. But it does raise a whole new range of power quality concerns, compatibility concerns. So there's a lot of exciting investigations here, and one of those is the issue of, what happens at these higher frequencies, the switching frequencies of the inverters and rectifiers that are used as for the electric vehicle chargers or the energy storage devices or the photovoltaic generation. And those higher frequency signals, and this chart shows signals in a range of about 4 to 50 kilohertz, just as an example. Those are frequencies that don't behave like the 5th harmonic or the 7th harmonic. The resonances can be very localized for those higher frequency conditions. So we have to look at the characteristics of the circuit in a local household or a local community, multiple households fed from the same transformer, and how local resonances might result in those higher frequency currents flowing into the power supply or the the electronics of another device, like a compact fluorescent lamp in the household. So a lot of research around the flows of these higher frequency signals, local resonances, and how do we do compatibility at this high frequencies? How do we evaluate emissions or the generation of higher frequency harmonic signals? And then how do we evaluate the flow of those signals? What kind of models do we need, and how do we evaluate it? So this will be something that you'll see in electric vehicle and inverter labs around the world, and we'll be hearing about some of those this week. So higher frequency harmonic levels, very important concern as we go forward. And I threw a slide in on microgrids because I think this is particularly important, that not only as microgrids become more and more popular as a resiliency solution, and we're seeing this in the United States right now with the wildfire concerns in the Western United States. We, in California in particular, we often have to disconnect entire distribution systems for 3 days or a week at a time. And those customers have no power for those 3 days or a week while the wildfire conditions are so dangerous. And the ability of individual buildings and households and communities to implement a solution of a microgrid or a backup for their loads during those periods is becoming kind of a standard solution. And that microgrid might involve PV and storage. There's going to be electric vehicle chargers in that microgrid, and load management becomes critical as well. So a lot of research around compatibility issues within a very small microgrid, as opposed to when those loads are connected to the main grid. And that's a whole different set of interaction concerns, system impedance characteristics, resonance possibilities that we have to evaluate when we're in that microgrid configuration. So that becomes very important going forward. Microgrid's absolutely critical. And of course, we've mentioned that electric vehicle chargers are right in the middle of this discussion. They are both a potential source of power quality disturbances. Harmonics, high frequency harmonics, impacts on the voltage regulation of the circuit, dealing with issues like hosting capacity. And they're also potential solutions. Can be a source of flexibility. The chargers can be combined with energy storage to become even a better source of flexibility and voltage management and load management on the grid. So this is a great time to make the deployment of electric vehicle chargers a solution to power quality problems rather than a source of power quality problems. And that's, I think, will be a very interesting part of the discussion all this week. And as we look at that and these power quality, compatibility concerns and research opportunities, monitoring is really key to understanding the interactions and the resonances and the potential concerns. Through one slide in here, we've done a lot of work over the years to be able to take advantage of monitoring to do more diagnostics rather than just benchmarking. Benchmarking, power quality monitoring for benchmarking is extremely important, but there's also opportunities to use that monitoring to provide an indication of potential problems with equipment. In this particular case, a power quality variation where there's a short interruption in the current and associated voltage sag downline from where that interruption occurs, was an indication that a tap changer on a transformer voltage regulator was failing. And actually seeing it in the power quality monitor that's happened in Austin, Texas, allowed the utility to go out and take that transformer offline and replace it before it exploded or caused a total outage of the transformer. So they saved a lot of money with their power quality monitoring as a result of that. And we're going to see more and more of that using monitoring for diagnostics. This is an example of a monitor that's built into individual circuit breakers at a household. This is one made by Eaton. It's called Energy Management Circuit Breaker, and so an individual circuit could have this monitor in it. It could be the circuit supplying an electric vehicle charger at the home, could be a circuit supplying a heat pump or an air conditioner, could be a circuit supplying a local energy storage device that we're interested in watching and characterizing, and allows us to understand everything from the load characteristics and the impact on the voltage and the grid, all the way to the response to disturbances or disturbances that might indicate a problem with that technology. And on the right, you're seeing a voltage sag that was recorded with one of those monitors on an individual circuit, and then we can see the response of equipment to that voltage sag, and our understanding and the potential for diagnostics and artificial intelligence applications becomes huge. So think about the wave of data that we're going to have available to do intelligent analysis with. Data from individual circuits and individual devices throughout the grid, as well as data from monitoring, on the distribution system, at the substation, at individual medium voltage to low voltage transformers. And I just like to emphasize that there's so much information in the waveform that when we're measuring power quality, it's more than just measuring the load characteristics, the RMS voltage characteristics and current characteristics, but actual waveforms are going to open up whole new areas of diagnostics for us as we get waveforms from everywhere in the grid. And the current waveforms in particular are so rich in diagnostics information about what happened, that having monitors that are always recording waveforms of voltage and current I think are going to be a critical part of future monitoring of the grid in general. We'll see web-based services based on that, and we're already starting to see it if you look at companies like Atom Power and others that are building solid state panels for industrial and commercial facilities as well as residential, that where every circuit is essentially monitored in detail, and we can apply diagnostics to that. So I think it's a brave new world for power quality monitoring. And finally, just wrapping up to reinforce this concept of compatibility. We have to look at analysis, standards, and evaluations at both sides. On the system side, where we have to understand what the immunity levels are for customer equipment, what the limits are that customer equipment that can inject in terms of power quality disturbances. And then we have to be able to evaluate the interaction between those power quality characteristics and our grid's impedance and resonance characteristics, and look at potential solutions on the system side, as well as solutions within the equipment and equipment standards as well. And measurements and monitoring is in the middle of the entire thing. On the customer side, we have to look at both equipment immunity, make sure our equipment that we design works with the level of high frequency harmonics that are out there, with the allowable levels of voltage distortion, with the range of voltage that's going to occur as we have more photovoltaics and electric vehicle chargers out there, and what are the solutions at the equipment level and the customer level that need to be implemented. So we're always looking at this balance, and compatibility and economics is in the middle of that. Where's the most effective way to make the investment for global compatibility from a power quality point of view. Tremendous opportunities for ongoing research, and I look forward to continuing to follow it and be part of it for years to come. And so I appreciate the opportunity today to kind of give a little bit of history and thoughts on this concept of compatibility, and hopefully we'll have a chance to talk about it some more during the best practices webinars this week. So thank you very much, Thijs, and the entire team for inviting me to do this initial keynote talk, and I look forward to a discussion here with potential questions from the audience. Thank you very much.
Oh, thank you, Mark. It was a really interesting presentation. A short question from myself. These new challenges, how do they compare with the challenges of the past? Is there a similar amount of effort that will be needed to mitigate it, or will it be completely something else?
Yeah, I think that the main point is that the challenges have changed. I don't know that it's more difficult or less difficult, but I think that, for instance, voltage regulation, just basic voltage regulation, is definitely more challenging now, because things like high-speed electric vehicle chargers and energy storage devices that might be participating in frequency regulation on the transmission system are actually connected all over our distribution system. So we have to look at the impact on voltage regulations in ways that we never had to worry about before. You know, we could design the system and the wire size and voltage regulators and capacitor banks, and we knew what the load variations were going to look like every day. And now it's much different. Similarly with harmonics, it's higher frequency concerns that we're just learning how to evaluate now, compared to kind of traditional lower frequency resonances that I think we've pretty much figured out, but still will be an issue as we go forward and you know, have to look at. So definitely the challenges have not gone away, but they have kind of changed to new emphasis.
Yeah, excellent. And about these higher frequencies, we're also talking about measuring equipment. But what do you recommend for this measurement equipment? What kind of frequencies should you be able to measure on the voltage and the current?
Yeah, that's a very good question, and it really changes the requirements for measurement equipment in terms of frequency rates of sampling and the need for anti-aliasing filters in the measurement equipment, and just the metrics in general. You know, do we characterize that whole 2 to 150 kilohertz range with a particular one index for all of it, or do we require evaluation of the full frequency spectrum of those signals and look at individual components? And if we do, how do we bin them? Do we bin in 5 hertz or 10 hertz or 100 hertz or kilohertz increments? It's a lot of questions there, and we're just, I think, just starting to scratch the surface in terms of the best ways to apply that. Maybe things like wavelets will become even more important. It was a topic of research for many years, and I'm sure it will show up again. And also, you know, reemphasizing just being able to look at the waveforms and evaluate the characteristics from a waveform basis. There may be approaches that apply artificial intelligence and learning techniques that to the waveform data that doesn't require wavelets or Fourier transforms to you know, become the basis of the evaluations. Sorry about that, but more questions than answers on my part.
Okay. Yeah. Well, there's still a lot of research to be done, of course, to get a good idea of what these kind of distortions will do and how we can measure them, etc. So I've got another question from one of our attendees, Shamista Bhattacharya, who actually will also be presenting tomorrow. She says, good morning, Mark. Nice to see you. Well, that's of course nice. I have a question regarding the discussion of adapting new emission limit values in the standard IEC 61002-4. This because of the new loads, such as EVs. Is that already implemented in the standard? Do you know what the status is?
You know, I don't know for sure what the status is. Mats Bolin, one of my good friends up in Sweden, has a team that's doing a lot of research in this area, and I know he's involved in continuing to evaluate how we can incorporate limits. Those are in the 61000-2 series is the equipment limit standard. So it's kind of how do we provide limits for the individual charger devices or inverters on storage devices in that higher frequency range. And that's, I think it's still a matter of investigation. I don't think that the limits have been implemented, but I don't know. I'm not on that actual committee. And I'd have to check with Matt and others. Maybe that will come up in the talks here this week, because I know we have some experts that are focusing in that space. But thanks for the question. I think it's critical, both in terms of what the limits should be for the equipment, then how do we verify those limits? What capabilities do test labs have to verify that equipment is meeting those immunity standards? And we've had limits around emissions that are radiated emissions that are high frequency limits for equipment in the past, and those we kind of cross over in this 2 to 150 kilohertz range between our conducted emission limits and our radiated emission limits, and it's a whole new category of testing capability that we'll have to have for the verification of compliance as we so coming up with the limits is the one thing, but then testing procedures and compliance, it has to kind of be done right in together with that, and that's the other challenge.
Yes. Okay, thank you for that elaborate answer. We've got time for one final question, because we're running a bit out of time. It's a question from Xavier Young. Hi Mark, what do you think the standardization of DC power quality indices, measurement methods, and LVDC compatibility level? Can we build these DC parameters based on AC experiences? For example, we may measure every 200 milliseconds for DC values as well.
Yeah, Xavier, good to hear from you. Good friend of mine from Power Quality Standards days and Power Quality Research from EDF. Fantastic. I think that's another category of compatibility work around DC grids. I mentioned microgrids in particular. Microgrids very often may have a DC grid as well as an AC grid, or maybe just a DC grid that is the basis of providing backup and service to loads that are dominated by rectifiers and inverters. So I think the same general approaches of compatibility can work, but it's going to have to be adapted significantly for DC characteristics in terms of both the system side and the response of the DC circuits, as well as how to evaluate the injection of signals that could disturb other devices connected to that same DC circuit. So another cop out on my part to defer to discussion here this week in terms of limits for the DC systems. Very good topic though, Xavier. Look forward to working on it.
Oh, excellent. Well, thank you, Mark. Well, we've run out of time. We need to prepare for the next presentation. So thank you for being our keynote speaker. And certain you will attend some of the other webinars, and well, please do. And otherwise, you can always watch them on our YouTube channel, of course. The next presentation will be from Martin Jaspers and Guillaume Goyen from Allego. It's charge point operator here in the Netherlands and in Europe, and they will share their experiences with DC chargers. And well, please join during this next webinar. It will start at 11 o'clock, so in about 10 minutes.
Thanks a lot.
Okay.